Welcome students. We are back with another lesson. In this lesson we'll continue with binding energy. So in our last class we had discussed what is binding energy. Then we had derived the expression for the binding energy. Next we derived this expression of the binding energy in terms of the mass of the proton and the mass of the electron, in terms of the mass of the neutron and the atomic mass. So, in today's class, we will derive the binding energy per nucleon. So, what is a binding energy per nucleon? The binding energy per nucleon is the average energy required to extract one nucleon from the nucleus. So, suppose you have a nucleus. Inside this nucleus, you have nucleons, which are your protons and your neutrons. So, out of all these nucleons, if I want to extract only one nucleon, whether be a proton or whether be a neutron, then how much energy I have to supply? So if I supply that required amount of energy, then either your proton will be emitted or your neutron will be emitted. Fine. So in this case, we have to apply only small amount of energy so that we extract only one nucleon. Okay, not all of the nucleons, only one nucleon. So we know your binding energy. What is the binding energy? The amount of the energy required to break the nucleon, to break the nucleus into its constituent nucleons. That means proton will be separated, neutrons will be separated, all of the particles will be separated. Fine. But if I want for an individual nucleon, then what I will do? I will divide this binding energy by the total number of nucleons. In this case, how many nucleons are there? 3. So how much energy each nucleon will take to break from this nucleus? It will be binding energy divided by 3. Fine. So from here we got the concept that if we want to break a nucleus having mass number A, then the binding per energy of the nucleon can be calculated by dividing the total binding energy by the total mass number. Fine. So I can write the binding energy per nucleon. Okay, I will use this delta B. This delta B stands for the binding energy. Fine, this is the binding energy. For this per nucleon, what I will do? I will add a n here. So this will make the total binding energy per nucleon. And my total binding energy per nucleon can be written as the binding energy divided by the total mass number. Fine. So this is the expression for your binding energy per nucleon. So we know the binding energy in terms of the mass of the proton, the mass of the electron, the mass of the neutron and the atomic mass can be written like this. So let's use this formula there. So my binding energy per nucleon can be written as the Z times the atomic number times the mass of proton plus mass of electron plus the total number of neutrons, that is mass number minus atomic number, multiplied by the mass number of the individual neutron minus the atomic mass, whole thing multiplied with c square. This will give us the binding energy, and if we divide it by the mass number, this will give us the binding energy per nucleon. Fine. So this is the expression for the binding energy per nucleon. Fine. So we have discussed what is your binding energy. Then we have derived the expression for the binding energy. after which we have defined what is a binding energy per nucleon, and then we have derived the expression for the binding energy per nucleon. So on the basis of binding energy, let's take a numerical. So in this question, let's read the question first. Calculate the binding energy of an alpha particle in mega electron volts. Given the mass of the proton as 1.007825 atomic mass unit, mass of the neutron as 1.008665 atomic mass unit, mass of the helium nucleus 4.002800 AMU, and finally the 1 AMU in terms of energy can be written as 931 mega electron volts. So they have asked us to calculate the binding energy of alpha particle. Okay, before we start this numerical, first you need to know what is a alpha particle. Alpha particle is nothing but the nucleus of the helium atom. Inside the nucleus of the helium atom you have two neutrons and you have two protons. But what is the difference? The two electrons which are revolving around the nucleus has been removed. So that's why you see the charges +2. Fine. Forget about the charge for now. Just concentrate how many protons and neutrons are there. What are the number of nucleons? So for this alpha particle, what will be the atomic number? Since there is 1 and 2 protons, so atomic number is 2. What is the mass number? How many nucleons are there? 2 protons, 2 neutrons. So in total there are 4 nucleons. Hence the mass number is 4. So your alpha particle contains 2 protons and 2 neutrons. So what will be the mass of the 2 protons? The mass of the 2 protons will be 2 times the individual mass of 1 proton. Mass of 1 proton is 1.007825 AMU. Similarly, the mass of 2 neutrons will be 2 times the mass of individual neutron, which is 2 times of 1.008665 AMU. So what will be the mass of protons? 2.015650 AMU. And similarly, what will be the mass of 2 neutrons? 2.017330 AMU. So what should be the total mass of the nucleus? Inside the nucleus you have 2 protons and 2 neutrons. So what should be the total mass? So the total mass will be 4.032980 AMU. Fine. But experimentally, what is the mass of the helium nucleus? It is 4.002800 AMU. So in this case there is a difference of mass. This difference of mass is known as your mass defect, and its value is 0.030180. How you will get this value? You will subtract these two values and you will get the mass defect. Now what happens to this mass defect? This mass defect is being converted into the binding energy of the alpha particle. So how much will be the binding energy of the alpha particle? Okay, so you write down the mass defect here. It is 0.03180 AMU times C square. Okay, and you make a small correction here. 1 AMU is 931 mega electron volt by C square. Okay, now if you look, this is 1 AMU. 1 AMU is how much? 931 mega electron volt by C square. So substitute this value here. Fine. So I have substituted the value of 1 AMU. Now the C square and the C square get cancelled. So I have 0.03180 times 931. And this value, if you calculate, is 28.097 mega electron volt. So how much is the binding energy inside the nucleus of the helium atom or inside the alpha particle? It is 28.097. Fine. So this is one way to find a binding energy. Okay. The other method is using this expression. But we cannot use this expression here. Why? Because this expression uses the atomic mass. And if you see in this question, they have not given the atomic mass. Rather, they have given the nuclear mass. So what you have to do, instead of using this formula, the binding energy in terms of this atomic mass, use this formula, the binding energy which is given in terms of nuclear mass. Fine. So this is the binding energy per nuclear mass. So if I write this formula, it is Z, the number of protons, Z times the mass of protons, the number of neutrons minus the mass of neutrons minus the nuclear mass. Fine. So if you substitute the number of protons, it is 2. Mass of proton, they have given in the question. This is the atomic number 2. This is the mass of the proton they have given in the question. This is your mass number 4. This is the atomic number 2. Mass of the neutron is also given in the question. Then nuclear mass is also given in the question. Fine. So you calculate this. So whatever you'll get from here, okay, whatever you'll get from this part, this will be in the units of 1 AMU. Now, just like whatever we did here, we converted this 1 AMU into mega electron volt. Similarly, you convert this 1 AMU to mega electron volt by C square, this C square get cancelled, and then calculate the value. Fine. You will get the same answer. Okay. So that's it for today's class. Thank you. And if you have any confusion, please feel free to ask. I will re-explain it to you again. And in our next class, we'll discuss the binding energy curve. Okay. So again, thank you.